Hello, and welcome to Tech to Tech presented by KYZEN, where we will explore common cleaning questions and answers. Let's get started. I would like to introduce KYZEN's own Dr. Adam Klett.
All right, thank you, William, and thank you everyone for tuning in to this episode of Tech to Tech, where we're going to be talking about designing for cleaning in PCB manufacturing. So what do we mean by that? Well, we got to make sure that we take into account the cleanability of our designs before we send them to manufacturing to make sure that we avoid costly reworks or problems in the cleaning process down the line. So I don't think I have to spend too much time on this, but I want to start by talking about why cleaning is critical for reliability. Right? We know that there's plenty of evidence to support that residues, especially ionic contaminants that are found on boards, impact the reliability of those boards. Things like dendrites can form, corrosion can form, and especially in high reliability applications, that's not acceptable. Those residues will significantly impact the reliability of the board. And nowadays, especially with the challenges associated with miniaturization of parts, bottom terminated components, the challenges of components being cleaned is much greater than it has been due to certain design choices that are made. Now, there are cleaning standards like those of the IPC that tell us that we need to clean. And so we need to make sure that the designs that we make both comply with those standards, make a functional part, but then are also easy to manufacture because we don't want to design something that is very difficult or expensive to manufacture. And then the last part about that is the reliability and cost implications. Again, if you create a design with a seemingly simple choice that ends up costing a lot of money in the end because it makes cleaning much more difficult, right? We want to try to avoid that. So there are a series of design considerations that I have here that I'd like to share. And although this is not an exhaustive list, right, here are a few points to consider. The first is going to be the standoff height and the component geometry. We'll talk about each of these in a lot more detail, but essentially the higher the component is, or the simpler the geometry of the part is, the easier it's going to be to clean. Also, component placement and spacing. You can imagine that placing components very, very close together is going to make it much more difficult to get that cleaning fluid in between them, underneath, and then get everything back out again. Also, things like the solder mask and the silkscreen, although they might not seem like they can affect cleanability, they can have a significant impact on our ability to get fluids underneath the component, clean out all the residues, and then get everything back out again. Also, same thing with trace racking. The traces underneath components can cause significant problems if it's not done right. And then vented components can also cause an issue. So we need to consider component choice. And like I said earlier, early planning in the design process ensures that the product is as cleanable as possible to minimize the process complexity and the process costs. All right, so first, let's talk about standoff height and component geometry. You can imagine that the higher a component is off the board, the easier it's going to be to get fluid underneath it to dissolve any residues that might be there and then get it back out. So there are a couple ways that you can do that. The first you can do is you can increase the trace thickness. It might not seem like a lot, but increasing that trace thickness by just a little bit is enough to help, in some cases, get fluid underneath those components. Another trick that I've seen is people using plated thermal vias inside of ground lugs to help raise the component. They act as almost standoffs on that ground lug, raise the component up. Also consider component geometry. There are components like leadless devices or devices that have complex termination that can really restrict how the cleaning solvent can penetrate underneath the component. There are also components with cavities inside of them or on the underneath side where there are things like passives that get included onto the package on the underneath side that end up trapping fluids or residues that make it much harder to clean. The next thing I want to talk about is component placement and spacing. Right. So first, shadowing reduces fluid access and can potentially leave residues behind. So shadowing is when we have a large component next to a low standoff component, or a low profile component like this. And this tall component shadows the ability of the cleaning fluid to get underneath this smaller component here. So this area right in here is very difficult to clean. Also, the clearance around those low profile components allows better spray impingement to get in there and get the cleaning efficiency. Another thing that you can do that might help a little bit is to align the components on the board. There are plenty of reasons why you would want to keep components in nice lines, kind of like a grid, as opposed to haphazardly placed at different rotations and things like that. Cleaning is not normally one of the big reasons that there are cited for doing that, but it does help a little bit. Also, proper spacing helps reduce, not only helps reduce rework and increase cleanability, but it also will help the inspection costs, right? You know, and imagine that if we can put a little bit more space between our components, it's easier for the fluid to get in there, clean the residues out, easier to rinse out, and then we can also see it much easier when we go to do the inspections. All right, next I want to talk about traces, solder mask, and silkscreen. So these three are seemingly innocuous. It's hard to imagine that these design criteria, it's hard to imagine that these parameters might actually affect the cleanability because they're so small. So for example, traces underneath components. These traces are very, very small, right? You might think, well, it's such a small trace, how is this going to impede the fluid flow underneath that component? Well, it might surprise you, but it actually can, because especially if you have very, very low standoff components, we're talking, you know, under 1 mil. I mean, even a tiny impediment like a trace can block fluid flow or significantly impede it from being able to get underneath the component. And it's not necessarily about completely blocking it. It can also, the effect on the fluid flow through it can significantly affect the cleanability. Right? Also, solder mask dams can block fluid entry, and you might create dead zones where residues or cleaning fluids, non-volatile residues, can accumulate. Silkscreen is another thing that a lot of people don't realize is hurting them. So in the picture that I have shown here, you can see that we have a component here. Looks like there's it's a 14 lead component, and underneath the component in the pattern, they have this silkscreen rectangle underneath the component. Well, I'm going to argue that that's not necessary at all, because one, that component is being placed with a pick and place machine, and that rectangle is not visible after the component gets placed down. So it's not used in any sort of inspection. It's really just an aesthetic thing that was put there by the designer of that component land pad. Well, even though it's very small, that silkscreen can still affect the fluid flow, just like the traces can underneath that. And so you want to make sure that you keep out silkscreen as much as you can from underneath those components, so we don't affect the fluid flow. Also, vias under components, kind of like the one that I have shown right here, without the proper fill, can create cavities that can trap flux or other residues, and it makes it easy, or it makes it harder to clean out. All of this is to say that we need to make sure that we provide accessible paths for the fluid to get in, do its job, and get rinsed out without trapping anything and interrupting that fluid flow. All right, now on to vented components. Vented components are pretty ubiquitous nowadays, and it's hard because they allow cleaning fluids to get trapped within them very easily. Imagine there's a picture here where you can see a lid. This has vents in the sides of them to mitigate that issue, but some have just a single hole in the top where fluid can get in, but it can rarely get out. And this causes reliability risks, especially over time. So if you place vent holes on top surfaces that can be blocked with either peelable coatings, stickers, things like that, that is the best thing to do if you have to use a vented component, or if you're lucky enough to be able to change the design of the lid, which although most people aren't, if you can, using a lid design like what I have shown here, where we have large openings for the fluid to get in and these openings happen to be on all four sides, so the fluid can get in. It has multiple ways to get in, multiple ways to get out, do its job without leaving residues behind. All right, so now I'd like to share an example of how a customer had issues with the design regarding component selection that could have been fixed had they known about these compatibility issues to begin with. So the challenge was that a major electronics program had issues actually with the components having compatibility issues during an aqueous cleaning process. It wasn't necessarily a chemical compatibility issue, but a cleaning process issue in general, right? Certain parts showed risks of damage during exposure to both the water and the high heat involved in the drying process. So KYZEN conducted IPC 9505 based compatibility testing and worked directly with the component vendors of the part to first identify the problem and then identify alternate parts that were able to withstand the cleaning process without the degradation issues. So what happened? Well, the customer was able to adopt these revised component sets. They eliminated all of the wash-related failures, and they established a pre-screening protocol because of this for future designs to ensure compatibility early in the VFM stage. Imagine an entire board can't be cleaned because of a single passive component on the board. So with that, I want to talk about some key takeaways from this. So biggest thing is make sure that you incorporate cleaning considerations early in the development of your boards if you're going to be cleaning them to prevent any either costly redesigns, engineering change orders, and failure analyses to make sure you enhance the reliability of those products, right? And that's going to include things like ensuring that fluid can access and get out of everywhere where there might be residues, specifically underneath components, low standoff components, and things like that. And so allowing adequate standoff height, spacing the components apart from each other, and addressing issues with vented packages can significantly improve the cleanability of your boards. Also, adjusting solder mask features and the Silkscreen can significantly improve cleaning effectiveness underneath those components and product durability. Also consider component compatibility, like what we talked about in the last slide, right? There are certain components that just don't behave the same as others in any wash process. It doesn't necessarily mean it's a chemical incompatibility, but a wash process where things like water entrapment or high heat or things like that can cause degradation of the components. And so you want to make sure that you don't utilize those types of components if they are going to be cleaned at the end of your manufacturing process. So lastly, we want to make sure that we use objective tests and collaborate with experts to confirm that, one, the cleaning processes are effective, and two, that they adhere to our industry standards like those of the IPC. All right, so now I'd like to talk about some frequently asked questions that we get. So one, why can't we just rely on no clean fluxes instead of designing for cleanability? It's a great question. We hear it all the time. And I like to say that just because the flux is called a no clean flux, it doesn't mean do not clean. It's not an instruction not to clean them, because there are plenty of literature and published papers out there that show that even no clean fluxes under the right circumstances can still cause failures. And so we don't want to have to rely on that. Second, what's the most cost-effective design change to improve cleanability without impacting performance? That's a tricky one because it's all going to depend on the design that you have. But I would say that one, getting rid of Silkscreen is probably the easiest to do because it's literally just a layer that you hide. You don't need it. I'm going to argue that no one needs that nowadays, unless you have maybe a few components, labels, or something on the side of the board, but it doesn't need to be underneath components. Also, if you have the ability to space the components apart from each other, that can be an easy change to make. You don't have to actually change components. You don't have to change much about the manufacturing process. It's just spacing the components out a little bit farther. Now, I do realize that a lot of these suggestions, some people might not be able to actually do that. For example, let's say you're making hearing aids and you can't put the components farther apart from each other because the entire assembly has to fit inside of an ear, right? So you can't. But that brings me to the next thing. Like, how do you validate that your cleaning process is effective for complex assemblies where you can't necessarily take all of these suggestions that I'm giving and incorporate them into your design? Maybe so you have to put the components closer together, or you have to use a certain component that has a very, very low standoff and you can't lift it up. We recognize that. And that's just going to mean that you're going to have to work with either your cleaner or work with a testing facility to make sure that you do the right testing to make sure that you qualify that cleaning process. And that's going to utilize something like SIR testing, using an SIR test house to make sure that the boards that you're building meet the IPC standards. All right, so with that, I'd like to thank you for your attention, and I hope that this has enlightened you on different design aspects about the design for cleaning and how keeping design for cleaning in mind at the beginning of the design process can really improve cleanability and improve the output of your manufacturing process. Thank you.
Thanks, Adam. Thank you guys for watching this Tech to Tech session. If you would like to discuss this topic further or have any questions not answered in the session, please contact your local KYZEN regional manager or send an email to tech@kyzen.com, and we will have someone follow up with you as soon as possible. And if you like this video, be sure to follow us on our social media platforms for more expert cleaning content.